Hello and welcome to our video solution for problem 17 from Superquiz 3. This is the final problem from that Superquiz. This was an optional question, the second one which tackled the fundamental theorem of arithmetic. And this is very similar to a problem we had on the previous Superquiz, where we were asked to show how to use the fundamental theorem of arithmetic to find the greatest common divisor of two positive integers. And here we're just replacing greatest common divisor with the least common multiple. So the idea of the argument is going to be the same. Of course, we have to know what least common multiple means, and we give the definition here. So for two positive integers, a and b, it'll be the smallest positive integer that is a multiple of both a and b. That is, a and b should both divide that integer, and it should be the smallest such positive integer that a and b both divide. So if we want to use the fundamental theorem of arithmetic, we have to know what that says. And of course, FTOA is telling us that if you take any positive integer, of course we can extend that to negatives, but we're just going to focus on positives here. If you take any positive integer, you can write it as a product of primes, but not just that you can, but you can do it uniquely. So there's only one way to write it as a product of primes, in the sense that the primes will be the same, and the number of times those primes show up will be the same. Of course, you could order them in lots of different ways to make it look different, but it's really not different. So what we can do in this situation is we start with two positive integers, a and b, and we can write down prime factorizations of those integers. So I'm going to start with a and b, and I'll write down prime factorizations. Now, there's no reason to believe that the prime factors of a and b are going to be the same. However, what we can do is just take the collection of all primes that show up in the prime factorization of a and all primes that show up in the prime factorization of b and write those down. And I'm going to call those P1 through Pn. So I have P1 through Pn. Now this makes it look like, well, as I've written it now, it looks like a and b are the same, but it makes it look like the primes are the same. Now, of course, a prime might show up more than once, and so these are going to be distinct primes. And I'm going to let, say, alpha 1 be an exponent on P1, and beta 1 will be an exponent on the P1 for B. And all the way down here, I'll have an alpha n and a beta n. And the way I'll make it so that it doesn't actually mean that all these primes divide A and B is I'm going to allow for these alphas and betas to possibly be 0. So it could be that a prime just doesn't divide A, in which case the exponent will be 0. So alpha 1 through alpha n, along with beta 1 through beta n, are going to be non-negative integers. So they're possibly 0. And we'll just assume here that P1 through Pn are pairwise distinct primes. So pairwise distinct means if you look at any two of them, they're going to be different. So we don't want P1 and Pn to be the same prime, for example. Okay, and when we say prime here, we're talking about positive primes. Okay, now I claim that the least common multiple of a and b can also be written as a product of these primes raised to powers, and I'll call these powers gamma 1 through gamma n. Well, of course, I have to tell you what these powers are, where gamma sub I is going to be the larger of alpha sub I and beta sub I. So I'll give you an example. So let's say we had A is equal to 2 to the 0 times 3 squared times 5 to the 1 times 7 to the 4th power times 11 cubed. And B is going to equal 2 to the 5th times 3 to the 1 times 5 to the 4 times 7 squared times 11 to the 1. So the claim is that the least common multiple of A and B will be, okay, so we can write 2, 3, 5, 7, and 11, and we'll look at the larger of the two numbers. So here's 0 and 5, the larger will be 5. Then I have a 2 and a 1, so I use a 2, a 1 and a 4, so I use a 4, 4 and a 2, again I use a 4, 3 and a 1, so I use a 3. Okay, so that's the claim. That's how I'm going to build it. So in order to show that this actually is the least common multiple, I need to show that first, A divides this number, second, B divides this number, and third, that it's the smallest number, which is a multiple of both A and B. Okay, so proof. Well, by the fundamental theorem of arithmetic, right, we know this is the only prime factorization for A. So there's no question that A is going to divide this, because we can take P1 to the alpha 1 times Pn to the alpha n. And we can, so this is your A, and we can multiply it by something to get P1 to the gamma 1 dot 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 Pn to the gamma n. What do I multiply it by? Well, because gamma 1 is the larger of these two numbers, then it's either going to equal alpha 1, in which case I don't have to multiply by anything to get gamma 1, or it's going to be equal to beta I, which will then be a bigger number than alpha I. And so I could just multiply by the difference of these two. So my gamma I can just subtract the alpha I. Right? And I go all the way up here, Pn to the gamma n. Well, that's, I guess, a 1, not an I. So gamma n minus alpha n. So if I multiply Pn to the alpha n by Pn to the gamma n minus alpha n, I'll just get Pn to the gamma n. And the important thing here is, because I know that gamma I is always greater than or equal to alpha I, because it's the bigger of these two numbers, then these exponents are always going to be at least 0. So this tells you gamma I minus alpha I is always at least 0. So I'm really multiplying by an integer. Okay, and if I multiply these two together, I get P1 to the gamma 1 through Pn to the gamma n. All right, so I don't know immediately that this is equal to the least common multiple, but if I give it a name like little l, then I can see that A times whatever this number is equal to little l. And so we conclude that A divides little l. Similarly, well, we write down the exact same thing, only instead of alphas, we'll have betas. So similarly, B divides L. Okay, so we've shown that A divides L, we've shown B divides L. The next thing we have to show is that L is the smallest positive integer. Well, okay, it is positive, but we have to show it's the smallest number, which is a multiple of both A and B. Okay, so let's make an observation. The set, let's call it, I don't know, M for multiples. The set M of all common multiples of A and B is, and we should say all positive common multiples of A and B, is a non-empty subset of the positive integers. Okay, why is it non-empty? Well, we know that A times B is a multiple of both A and B. So we have a non-empty subset, and so there is a smallest element. Okay, so by the well-ordering axiom, M has a smallest element. And because it is a multiple of both A and B, then we know that when we write down a prime factorization, it has to contain all of the primes P1 through Pn. Okay, this again is by the Fundamental Theorem of Arithmetic. So it has the smallest element. So by FTOA, oh, and let's give a name to this element. How about little m? By FTOA, P1 through Pn all divide m. And in fact, we can go even more. We could say even more, right? If I look at P1, I know that A divides M. So P1 to the alpha 1 has to divide M. Right? In fact, let's write it down like this. So P1 to the alpha 1 has to divide M, all the way up through Pn to the alpha n. That has to divide M, because A divides M. And similarly, P1 to the beta 1 has to divide M, and Pn to the beta n has to divide M, because B divides M, and Pn to the beta n divides M, divides B. So these all have to divide M. Now, saying that P1 to the alpha 1 and P1 to the beta 1 divides M is a little bit inefficient. If one of these numbers is bigger, like say alpha 1 was a 3 and beta 1 was a 5, then it's a stronger statement to say that P1 to the 5 divides M than to say P1 to the 3rd divides M. So we might as well only choose the largest of them. But choosing the largest just means you're looking at the gammas. So this tells you that P1 to the gamma 1 through Pn to the gamma m, n, all divide M. But if they all divide M, then their product also has to divide M. So P1 to the gamma 1 through Pn to the gamma n, all divide M, right? Because these are relatively prime to each other. But this is precisely your L. So L is a multiple of both A and B, and it divides M, right? And they're all positive, so this tells you that L is less than or equal to M, but M was the smallest element in this set M of common multiples. So M was supposed to be less than or equal to L. And so we can conclude that L is equal to M. Well, what is M? It was the smallest common multiple of A and B. It's the least common multiple, right? Like we didn't say it at the time, but that's what M is. It's the least common multiple. So this tells you L is equal to the least common multiple of A and B.